Thank you very much. I regret that I cannot join you. I did join at this kind of conference 5 years ago, and I really enjoyed it. And this conference looks really impressive. It features my main interests at the moment. Lots of Moiré materials, fractional Chern insulators, and so on that I'm going to talk about, but also non-Hermitian physics that I think most people expected me to talk about. But now I found this very exciting. So I'll tell you about these 3 concepts that you can see pictured up here. First one is supposed to be about quantum geometry, then about anions, which you see in fractional Chern insulators, and then what does this all have to do with Moiré materials. So this will be based on a couple of papers that we have worked out during the pandemic, basically, together with 3 young, very brilliant persons. First is my PhD student, Ahmed Abouel Komsan, and my postdoc, Kang Yang. And then finally, my former postdoc, Xiao Liu, who's now assistant professor at Zhejiang University in China. So let me take you through these concepts, starting at the middle. So fractional Chern insulators are basically high temperature fractional quantum Hall states. And they have some other features as well. But let's go back to fractional quantum Hall effect. What is that? Well, it mainly occurs in Landau levels. Well, in graphene, you can see it also in strong magnetic fields, but that forms another type of Landau levels. So what do you need? What are the key ingredients? Well, you need topology, finite Chern number, and you need flat bands such that interactions can dominate. So in this setup in Landau levels, you need extremely strong magnetic fields and extremely low temperatures. And since this is an interaction-driven phenomena, the energy gap is set by the Coulomb interaction scale. And if you go through the math and look at what the magnetic length, which is the characteristic length in the Landau level is, it's inversely proportional to the square root of the magnetic field. That means that the gap is proportional to the square root of the magnetic field. So that means that you cannot enhance this temperature, which is typically less than a Kelvin, by very much. If you want a factor of 10 to 10 Kelvin, then you would have to have a factor of 100 strong magnetic field, and that's simply impossible. So the question is, are the lattice scale realizations such that you could get rid of this strong magnetic field and the low temperatures? Because then you would have interactions at the lattice scale instead. And we know from Haldane's work that you basically don't need a magnetic field. You need to break time reversal to obtain a Chern number. So the dream is that this would give us more robust experiments, maybe useful applications, topological quantum computers and so on that people have dreamt about for decades, and qualitatively new physics, perhaps. Well, one is still looking for arenas where this can actually happen. And recently, Moiré materials came up as a new promising platform. For instance, if you look at twisted bilayer graphene at a magic angle and align it with boron nitride, then you see that you can split these kind of nearly flat bands of twisted bilayer graphene into nearly flat Chern bands. They have opposite Chern number, but if we can concentrate to one of the bands, they have a finite Chern number. So if you dope and be within this band, this looks like a very promising arena for fractional Chern insulators. And there's no magnetic field here. Another example, which we also heard about yesterday, is tri-layer graphene aligned with boron nitride. And that also has flat bands with finite Chern number. And you can switch parameters such that this has either Chern number 3 or Chern number 0. So I think in this case, that one above has Chern number 0. So you can look at both cases. So it's interesting to look at the interactions in these systems. Let's have a very naive look at the energy scales of this problem. So Moiré bands, they are in some sense intermediate between Landau level physics and the underlying lattice scale. So Landau level physics is essentially continuum. The magnetic length is several hundred lattice constants, so you can forget about the lattice effects, they average out. But Moiré bands is somewhere in between. In this famous 2011 paper by Xiaogan Wen and his group, they pointed out that in principle, at least, if you're naive enough about it, you could dream up gaps of around 500 Kelvin for fractional quantum Hall states, fractional Chern insulators. But typical effective lattice constants in Moiré materials are perhaps 50 times larger or 60 times larger or something like that. So that would tell us very naively again that critical temperature could at least be 10 Kelvin, and you would also get rid of the magnetic field potentially. So it wouldn't get up to room temperature, but it would still be a huge progress potentially. So there is an unexplored regime of these systems, at least when we started looking at this a couple of years ago, because earlier experiment and especially theory focused essentially on integer fillings or weak doping. And experiments in theory pointed to ferromagnetism and valley polarization, so that was very promising for us and led us to study the problem of one band which is assumed to be valley and spin polarized. And then we project interaction, assuming that the interaction strength is stronger than the bandwidth. You have a projected Hamiltonian of this form. This is still a complicated problem because, of course, if we wouldn't project to a band, this would be trivial. You just place the particles far away from each other. But now you project into a Chern band, and a Chern band has one-year orbitals that have necessarily one over r² tails and so on. So it's still a very tricky problem. So that's what we set out to do in this early paper. And I told my student Ahmed that he would probably find fractional Chern insulators. But first results looked like a mess, and I guess he thought that I'd dragged him into a bad topic. So this is plotting the density as a function of momentum. And this is something that's standardly done in numerics. And if you have a fractionally Chern insulator, you would expect something that's fairly constant. In a finite size and in a lattice, it doesn't have to be constant, but somewhat roughly constant. Oops, this scale is totally off. There should be essentially 0 and essentially 1. Sorry about that. But you see, there was a huge fluctuation, and this all didn't look like a fractional Chern insulator at all. So far from homogeneous, no fractional Chern insulator. But what is it? Well, it looked to me first like more or less a random state. Then we thought a little bit about it, and thinking about this kind of attitude, a change of perspective is worth 80 IQ points. And since we couldn't increase our IQ, we could at least change our perspective. So we tried. So we tried describing the same problem in terms of holes instead of electrons. So let's make a simple-minded duality transformation. So let's C at momentum k becomes D dagger at momentum k. Okay. Then this projected Hamiltonian transforms into essentially the same thing. But since we need to normal order it again, we pick up a term from commutators, a single particle term. So you can explicitly calculate this, and it becomes a combination of these matrix element from the interaction. So it's a dispersive term in principle that's dependent only on the interaction. If there was no interaction, this would be just 0. And when one plots this, one finds that it's quite strongly varying. So here, for different cases, trilayer graphene on hexagonal boron nitride with Chern number 3 are in 0. and the twisted bilayer graphene at different parameter values. So there is some uncertainty in the literature which one is correct, but this one is more likely correct. So the interesting thing here that we find that if we plug in typical parameters for these materials, this whole dispersion that we generate from interactions can be about 5 times as large as the bandwidth of these nearly flat bands. So it's going to be a very strong term. And the more important thing to notice here is that in Landau levels, this is constant, while in Moiré materials, it turns out to generally vary and fluctuate quite strongly. So in Landau levels, you can calculate this and it becomes just a constant. And that's because we have translation invariance in momentum space or Landau levels. And that's because essentially real space and momentum space are essentially the same thing in the Landau level, not in general in the Chern band. Okay, so this gave us some insight that we have a strong dispersion plus the same problem again. So let's take this seriously and take this suggestion as a new parameter. So look at just a single hole problem. Then we know that if we plot the density of electrons, this would be totally filled, and then there's one hole. This is at a small system, and this is exact. So we have one, and then we just put the hole where it's most favored by this single hole term. And notice that this is very different from having a single electron, because a single electron in a flat band that doesn't interact, so it's massively degenerate. But a single hole can be formed in very different ways, and that has a dispersion. So this is a unique ground state of a single hole. So now, if we go away a little bit from the single hole, so here is 9/10 with a few holes in the system, and we plot this density as a function of this hole energy, we see it's nearly perfectly 1 and then going to 0. But there is some deviations here near what looks like a Fermi surface. And that deviation we can fix by doing Hartree-Fock on our initial ansatz. So taking a Hartree-Fock energy as our parameter instead, make this looks exactly like a Fermi liquid of holes. So this might not be so surprising. If we're close to a filled band, then this dispersive term would dominate. But it holds true very far away from this filled band. So this is it's the tri-layer Chern number 3 system. So here is something that looks almost like step function Fermi energy, but it has some deviations close to the Fermi level. Hartree-Fock again fixes this. And the filling fractions here are not just 9/10 close to 1, but also 1/2 and 1/3. So this whole dispersion seems to dominate physics even very far beyond where you would naively expect it to dominate. So this is the state we found, basically on the first slide. That's what looked like a mess. It's this kind of state. So we can do this at many different models. We can do tri-layer. These are these two panels with first just the whole dispersion and then the Hartree-Fock corrections. Then we do twisted bilayer graphene on hexagonal boron nitride with the most likely experimental parameters. We see something that's a little bit less clear here than we did here. But if we decrease one of the tight binding parameters, then we see it starts to look qualitatively different. So here are essentially straight lines. They have some inclination, but they're essentially straight. So we were thinking, if we want to find fractional Chern insulators, it's probably here where we should look, where we have something that doesn't look like a Fermi liquid in some sense. So let's look at this case. It's slightly off the ideal parameters, but let's look there anyway. Well, yes, then we find fractional Chern insulators. So this is twisted bilayer graphene aligned with boron nitride. And we find FCIs in a clear-cut way only if we have slightly weaker interlayer tunneling than in current experiments. So there is ground state degeneracy on a torus, spectral flow of ground states, particle entanglement spectrum, everything is consistent with the fractional Chern insulator. So here, for instance, in the particle entanglement spectrum, there's a prediction with a few thousand states below a gap, and you find exactly the counting of these states per momentum sector and the total as well. And the gaps that numerics give out is essentially 10 Kelvin. So a bit cold, but not super cold anymore, so to say, and no magnetic field whatsoever, but at slightly different parameters. And we came out of this, we came out with this paper very shortly after, a couple of weeks after. There was papers by the MIT group and by Harvard group showing that first, there is spin polarization indeed. If you take spin into account, you find FCIs as well. We assumed it. And then there was this nice work by the Vishwanath group, which find a solvable limit by putting one of the tight binding parameters to 0, basically. Then you can find exactly Laughlin state if you take a very short range interaction. Our numerics, by the way, is for very realistic screened Coulomb interactions. And last year, in fact, published 15th of December, and I think the preprint was out in July, by the Harvard and MIT groups, there were experiments finding fractional Chern insulators in magic angle twisted bilayer graphene. Similar to our prediction, but they actually had a magnetic field, a weak one, which they claim do not change the provenance of the flat band or the Chern band, but it changes quantitatively properties of the band in a similar way as our decreasing of the interlayer tunneling did. But it turns out that applying a magnetic field is more feasible experimentally, at least for first experiments. So here is one plot they did. They looked at the parameters. Here is like interactions between the layers compared to within the layers. And here is a magnetic field. So you can see what we did was essentially changing along this axis in our theory paper, while the experiments changed in this direction by applying a magnetic field. And you can see that actually at the bare problem, we find there is a charge density wave. But if you change either of these parameters a bit, you can get into a big area of the phase diagram which hosts fractional Chern insulators. So that was really great, and of course this beautiful experiment was published in Nature. I should say though that it's not the typical Hall conductivity measurements or that you like to have. It's more what we saw on the talk yesterday afternoon with this local incompressibility. Nevertheless, it's convincing evidence that there are fractional Chern insulators in these materials. But as theorists, we can move on quicker to look at other materials. We don't have to set up the experiment. We can just think about different models. So one promising such is twisted double bilayer graphene. You can see this paper, for instance, where they did this. This has a very interesting tunable band structure, which you can tune by both the twist angle and a gate potential. And you can see that you can get Chern number 2 bands that are relatively flat, Chern number 1 bands, and Chern number 0 bands. So here, for specific values of gate potential and twist angle, here is a flat Chern number 0 band, a relatively flat Chern number 1 band, and a very flat Chern number 2 bands. So it will be interesting to see what interactions does in these bands. And well, it turns out to be really an abundant platform for fractional Chern insulators. Some actually do not have a direct counterpart in Landau levels in fractional quantum Hall states. So this is all contained in this paper. So we find in a Chern number 1 band, we find Laughlin, hierarchy states, and spin singlet FCIs. So if we include again the spin degree of freedom, it's not spin polarized as usual fractional Chern insulators are, but it's a spin singlet state. And in a Chern number 2 band, we find a 1/3 fractional Chern insulator, which has a funny interpretation of negative flux attachment. But since Landau levels always are Chern number 1 bands, there is no direct correspondence of this in the ordinary Landau level case. And we find that you can get rid completely of the magnetic field, it seems, and much of the cold temperatures, potentially down to 5 Kelvin. So very brief look at the evidence for this. So one can find again ground state degeneracies for different system sizes, spectral flow, scaling of gaps, entanglement spectra, for instance. So this is examples for 1/3 in Chern number 1 band. Show a little bit less for the others. Here's the Chern number 2. It took us a while to understand what goes up with the spectral flow, but it's all fine. And there are spin singlet states and spins polarized states. So if you plot the total spin sectors, you will find that in the spin singlet state, there's something uniquely picked out. It's the same spin 0 sector for all the low energy states. While in the spin polarized case, it doesn't care about the total spin. It's just polarized. You get the 2s plus 1 fold degeneracy of these ground states. That's what we see. So let's now go to the first part of the talk, the first part of the title, and this quantum geometry. And it's a more recent work with Ahmed and Kang. And this goes back to the quantum metric, so-called quantum metric, which contains 2 parts. One is the Berry curvature, which I guess most of you are familiar with. And that was also what was used in this Nature paper to quantify when we get fractional Chern insulators. But there's also another part called the Fubini-Study metric. And this is the thing that we find microscopically enters the interactions, essentially. So what is this Fubini-Study metric? Well, it has a natural interpretation in terms of distance between Bloch states. So if you take 2 Bloch states at different momenta in a band and look at them on the Bloch sphere, then you can associate a distance between them. And that distance squared is defined as 2 minus 2 times this mu dagger at, well, k prime times mu at k. So if these are the same, of course, then the distance is 0. So that makes sense. And at small separations q, this defines a metric, G. And in fact, this appears directly in the single hole expression. So you can write the single hole term, which we actually have to throw away some periodic contributions due to the Moiré bands. It's a bit technical, you can see in our paper. But this is the main part. And this looks exactly like what you have here. So you can approximate this for small separations with this thing. And to make it positive definite, which it has to be, you can just exponentiate this piece. So this is what we do. So it's V of Q times essentially Q squared and this metric.
Emil,
you can do Hartree-Fock calculation, which... Sorry?
You have 10 minutes to talk more.
Okay, good. That's perfect. I will manage with that. So now let's look, instead of just looking at the whole energy, we can look at this metric because they are closely related. We can look at the single hole compared to the metric, and we see that here is the log trace of the metric, that's the simple measure, and here is minus the whole energy. And we see that these have very similar shapes. And we can also look at the Chern number 3 band. They are all, again, very similar. So this is the Fubini-Study metric, or the log trace of it. And here are the whole energies. And this assumes some very realistic interaction again. So we could do what we did before, but instead of having whole energy on the x-axis, we can take log trace of the metric, and we do the same thing, and we see in general some behavior and often some step, some Fermi function. Of course, you would have to do Hartree-Fock correction again on top of this to make it look more perfect. We didn't do that here. I even included some very bad example to show you that this doesn't always work. It is a tendency, and it very often works. And you can see in general in each of these plots that you have lots of points here in the upper left corner and points in the lower right corner. So there is some dependence very generically, but it doesn't always work, of course. And that's good, because if this always worked, you would always destroy fractional Chern insulators. But the trace of the Fubini-Study metric dictates low energy physics to first approximation, something you can always start from in these systems. So how about fractional Chern insulators versus non-fractional Chern insulators? Well, you can take a model which contains both, and it turns out that things are a little bit subtle. But here is a trace of the metric, and here is the occupation number. And here is a model which is known to have a FCI, and it still has this tendency to follow the metric. But it doesn't do so in a dramatic way, as a charge density way, for instance, which turns out to follow the metric on much larger scales. So the key here is to find models for fractional Chern insulators which has a small dispersion in the trace of the metric. So the metric should be as constant as possible to get fractional Chern insulators, because then there is not room enough for the density to track this dispersion, track the metric. But I'm basically done now with stuff that we have done, and I wanted to give you a few examples on things we want to do. But if you do them before us, and then I congratulate you, and I think there's a very interesting outlooks. One is non-Abelian states, because they have not yet been confirmed. It's easy to find six-fold degeneracies suggestive of more reed states with Majorana fermions, but these never pass all FCI consistency tests. With Xiao, I developed for about a decade various tools to check if these are really FCIs. And had we not done that, I'm pretty sure we would have published something saying that there are more reed states. But since we did all the consistency checks, we could disprove ourselves before publishing. But it doesn't say that this could still be possible, but there are better models. So there are many platforms to check, and one can get good insights from looking at Fubini-Study metric, or the full single hole problem, or projected two-body problems also is very interesting to look at. And they are much quicker than to calculate the full many-body properties. So there are like cheap ways to scan many different materials. We haven't had time to do that yet. We've scanned a few, and they always fail at some of the tests. Another thing is, of course, these materials are mostly known for novel non-FCI physics. And it can be interesting to look at this from a perturbative approach, starting from the single hole dispersion or from the fluctuating geometry. So if you look at these single hole dispersions, and at least in twisted bilayer graphene, if you change the doping, you can see that there are phase transitions where the shape of the Fermi surface changes, or Lifshitz transitions. And there are Fermi surface instabilities in terms of nesting, charge order, superconductivity, and so on. Some of this was explored by Andreas Leuchli's group, mostly from a numerical point of view, but very beautifully. But one could do this more systematically, diagrammatically, and we found some interesting preliminary work on this. And there are almost endless possibilities with this. You know, we can try to explain phenomena that you find also in other Moiré materials and other flatband systems for that matter, because these things that I told you about with the single hole dispersion and so on, that's generic to flatband models. It's not specific only to Moiré materials. It turns out that this connection to quantum geometry holds much better in Moiré materials because you have many sites in the unit cell. And well, I could talk to you in private about that, but one can show that it's much more promising in the Moiré systems than others. Finally, these systems look like a perfect setup for genomes. So these are inspired by earlier ideas of wormhole-like twist defects, because we know from the work by Wen and Yui in 1990 that the degeneracy of topologically ordered states on manifolds depends on the genus of the manifold. And Barkashley and Chi pointed out that you can use this to have lattice defects changing the genus of a material. So if you have a bilayer system, you can start making dislocations connecting the layers and thereby changing the genus. And then you change the ground state degeneracy, which is like having a finite quantum dimension of a quasi-particle. And they have also shown in subsequent work that these obey non-Abelian statistics. I'm not sure how to braid the lattice defect, but still it's a very cool idea. We did some work on this in hypothetical collatum setups with Hofstadter models and so on, and there you can find defects that carry these quantum dimensions and are essentially genomes. It turns out, however, if you have flatband models and create defects, you likely create in-gap states that are located to the defects. And then you have to look at the so-called topological shift of the model you want to mimic. And then you may have to take this state either down or up to bring them to the flat band. That's what we had to do in this case. We bring them down to the flat band and then look at that manifold. Unfortunately, since these are localized, you can do that with the local potential without destroying the band structure. And then within this new effective band, you can get genomes. So question is, how about the Moiré setting? And the first thing to do is to look at the single particle problem. What happens with mid-gap states, what you have to do with the mid-gap states, can you control them, and so on. So this is on the to-do list. But let's conclude. So Moiré materials is a very new and versatile platform for fractional Chern insulators. There's a major impact of quantum geometry, and that's bad news in a way for fractional Chern insulators. You can find them, but very often you will have an intriguing competition with other phases. And there's really still a lot to discover. There's just a few groups that have worked intensely on this, but they're already very beautiful experiments and nice theory. We have written a review chapter for an encyclopedia book recently that we put out on the archive. It's more general on fractional Chern insulators, but we mostly focus on Moiré materials because that's what we find is the most promising platform for FCIs at the moment. And well, if anyone that hears this is interested in doing a postdoc, well, let me know. We have a few positions open. Thanks.
Okay. Yeah. Thank you for the nice talk. And the seminar is open for the questions. I have a short question. So you said the Moiré states is not found in the twisted systems in numerics. Is it because the non-abelian states are more fragile than the abelian states, like in the Landau level cases?
That's right. So you mean the non-abelian states were not found? Yes.
Yeah.
Yes. So they're more fragile and they need slightly different form factors. So the reason why you find them in Landau levels, you don't find them in the lowest Landau level.
Right.
You find them in the second Landau level, and even there they are fragile. So the question is, how do you find Moiré setups that are more like second Landau levels? There are very nice ideas about that, how to do it. But the question is, how to find that in a realistic, fully realistic model. And I think it's doable. It's just that we haven't found the right and realistic model yet.
Oh, I see.
There are toy models around, but nothing realistic.
I see. Thank you. Other questions? Okay, Pamjong.
Thank you for a very nice talk. So you showed that the whole dispersion and the Fubini-Study metric shows a similar behavior. Is there a physical way to understand the relation between them?
Well, in principle, there is not much of a relation, except this thing, that if you look at the expression for the whole energy, it contains this mu dagger mu term that multiplies, of course, the potential, and potential can be anything, but for realistic potential, this turns out to be the important thing. And this thing occurs in the definition of the Fubini-Study metric.
Is it valid in general? I mean, or your system has some special property that
of course, there are several approximations involved here. The Fubini-Study metric only dictates the short distance behavior, small q, and that may or may not always be dominant. And if you have a very strong variation of q on the potential v, also this might also kill things. But for realistic systems, this turns out to work very well, surprisingly well.
Okay, thank you very much.
Okay, okay, next. Yeah.
I have a question. So we know that to do the interaction in the quantum hole, we need to project to the lowest Landau level. And here it seems like you need also to project your wave function to the flat band, right?
Yes. Well, that's for numerical convenience.
So that means it's not easy to write everything in terms of like in momentum space. If you do this like exactly, it's not easy to write the interaction in the momentum space because you need to project the wave function to the flat band first, and how you do the Frege form in this way.
Yeah, that's a good question. So in principle, in this case, we go to an effective few band low energy limit, and based on Dirac cones and so on. And that's standard in this system. So you get some sort of, for twisted bilayer graphene, for instance, you go to an 8-band model and so on. And this is enough. Of course, to look at a fully microscopic model, that's what people do for fractional Chern insulators, because they're the systems, well, in the past at least, when you just have 2 or 3 sites or so in the unit cell, then it's very simple to do it. Here you have to do some approximations on the way.
And my other question is, you mentioned some kind of flux attachment. Do you mean that you have also the composite fermion picture for this fractional Chern insulator?
Yes, for that one, there is a paper by Gunnar Muller and Nigel Cooper in 2015 or so, where they look at composite fermion theory for higher Chern number bands. So,
not in your model.
Well, this is the interpretation So in our case, we don't have a toy model that can be solved exactly, but this negative flux attachment composite fermion state has lots of properties that you can calculate. And we can numerically calculate the same properties, and they turn out to be the same. So it's a strong conjecture that it's that state in that universality class.
And the last question is, you mentioned using the Hartree-Fock, but the system is strongly interaction. So why should we choose Hartree-Fock?
Yes, that's a brilliant question. That's the big surprise, right? So you don't expect to get something from perturbation theory when you have a flat band. But it turns out that you do. And one way of seeing this, when you do the particle Hall transformation, that reveals that there is effectively a single particle term when you view it in a different basis. But it's the same problem.
Okay, thank you.
Okay, I see the question from Zoom, Matthias Schroer. Yeah, you can ask a question.
Yeah, hello, hi, a very nice talk, very pedagogical.
Thanks.
Beautiful. So I have maybe the following question. So if I understand correctly, this Hall dispersion, the Hall dispersion that we're talking about comes from the fact that, you write down an interaction which has the form like, density times density. Also after you project it to, just one band or two bands or however many bands you keep.
And,
right?
It's normal ordered, that's the key.
And it's normal ordered, yeah, exactly. And now, of course, there's, I'm sure you've seen this. I mean, there's quite a discussion whether this is really the only way we can do it, right? There's a discussion that, you project out these bands and that can actually modify the interaction you have at the end, right? So, yes. I mean, in Hartree-Fock, people call this a subtraction point, but you can call it whatever you want. It's ultimately just the definition of how you write down the model. And of course, you're using exact diagonalization as far as, in most of this calculation. So you exactly solve the model, which is great. But my question would be, have you also checked like other versions of the interaction? So for instance, there's one like other extreme limit where usually you write it like a rho minus, 1/2 sort of identity times something that is only finite if you're on the reciprocal lattice, which would, I think, give you some particle Hall symmetry and then would get rid of this Hall dispersion. So my question is simply, have you checked with your exact methods whether in some cases you get rather different results with this interaction, or have you just happened to not have done that? I'm just interested. I think it's an interesting question.
I think that's a great question. It's very interesting. And I'm pretty convinced that this is the physical case that is normal ordered. This is the physics, because just one electron doesn't interact with itself. And that's a very profound thing, but one hole, that's many interacting electrons in a band. So I think there's a physical difference. But
there is, yeah.
And I'm sure there would be a huge difference if we would use the normal ordered thing, or non-normal ordered that you suggest. It would be very interesting. But I think also the experiments that the Harvard group did speaks in the favor of this normal ordered thing, because they found a similar phase diagram. They also needed to go away from this limit which you have without a magnetic field, and they show that either you apply a magnetic field, or you go the other way and change the interlayer tunneling. But yes, I still think it's worth doing this test, and in particular confirming it with experiment to see what's going on. It's very well worth doing. Thanks. It's a good question.
Okay. Thanks for answering all the questions. Let's thank the speaker again. And